We are now ready to look at the third learning objective in our kinetics lessons. And in this learning objective, we're going to be examining what's called a rate law. We're going to identify the necessary components and parts of the rate law, and we're going to, if given a rate law, be able to determine how the change in concentration of reactants will affect the rate of the reaction. So here's the definition of a rate law. It expresses a relationship of the rate of the reaction to a rate constant and the concentration of reactants. Okay, this is different than a rate expression, which we use changes in concentration and changes in time. This has nothing to do with time in there. It has a rate constant and it has only the concentrations in there. So here is a reaction, a very generic reaction of A and B as the reactants and C and D as the products. The rate law for this reaction would look like this. It has a rate constant K, so that's what we use always for the rate constant is a lowercase k, and it's a concentration of our reactants, A and B, raised to, and see the word sum, raised to some powers. It is not the same powers as the coefficients. My coefficient here was A, the power is X. I'm using a different representation here. X and Y can only be determined experimentally. You cannot look at a reaction and know what those powers are. You have to perform some experiments to determine them. Now we're going to learn how to determine those powers in our next learning objective, in our next unit, our next series of lessons. But for now we're going to examine some and see how we can use that rate law to make a judgment about the reaction. Now here's a reaction, A plus B going to C plus D. I have one coefficient, and somebody went and did some experiments. And they noticed that as the reaction takes place, we see and they did it and monitored it many times. They saw that at certain concentrations of A, the reaction took place at various rates, and they found a nice straight line. This straight line tells me it's a linear relationship and tells me it's a direct proportionality. So we could say that the rate of the reaction is directly proportional to A. Or we could replace that proportionality symbol with an equal sign and say that rate is equal to, and we put the constant in there of K, equal to K times the concentration of A. So it's technically raised to the first power there, but when it's raised to the first power we don't write it down. So as we examine this, what does it tell me? Well, K is called the rate constant. I've already told you that. Let's talk about the units of K. The units of K change depending upon what rate law we're dealing with. And it's obtained by solving the equation for K. So if we took rate divided by the concentration and put the units in for rate, which is always molarity per second, and the units for concentration, which is, in this case, well, it's molarity, then that would give me, with the molarities canceling, the units for K. You can also obtain a value for K. So if you actually knew a value for rate, how fast it was going, and a value for A, you could obtain a value for the rate constant. Now every time the reaction takes place, and this is key, at a constant temperature, the same value of K will be obtained. K is a constant. But know that this constant is only a constant for a reaction taking place at the same temperature. If you go and change the temperature, it will change the value of this rate constant. We'll see how and why in lessons to follow. Let's look at a very specific reaction. Here is a reaction, NO plus hydrogen producing nitrogen and water. Now, somebody went and did the experiments. They did the monitoring, and they found that the rate law was this. Rate is equal to, and there's rate constant K, NO raised to the second power, and H2 raised to the first power. Note again, this is not the same as the coefficients. This one happens to be the same. but this one is a 1. So be aware of that. Some language that goes along with rate laws is this reaction is said to be second order in NO. The order is the power. So second order in NO. It is said to be first order in H2. So that's just the language we use. And it is third order overall. And to get that, you take the 2 plus the 1 and you get a 3. Third order overall. There can be zero orders. If the concentration of a substance has no effect on the rate, then we'd say it's 0th order. Orders can be fractions. Orders can be all sorts of different things. They could even be negative numbers. I didn't put that in here. Could be negative. Just be aware of that. Okay, so let's look at this rate law. Let's say we go in here and do the reaction twice. And in those two reactions, we don't change the NO concentration. But we double the H2 concentration. Think about this reaction. If we kept this part the same, but doubled the H2 concentration on those two reactions, how would that affect the rate? Would you say that the rate wouldn't change if we doubled the hydrogen concentration? Would you say the rate would double, the rate would be cut in half, or the rate would quadruple? If you said it would double, you'd be correct. One way to do that is to plug some simple numbers in. Let's do the reaction once, and let's do a 1 and a 1. And let's do it a second time. We don't change NO because it's remaining constant, but we double this number. That is going to give me, for this one, just K. For this one, 2K. Let's ignore that little guy there. So we see that it is doubling the rate. Okay, let's try it another way. Now we're going to do the experiment, and we are going to do it twice. We're going to keep hydrogen constant, but we're going to double the NO. Now if we do that, would the rate stay the same? Would the rate double? Would the rate be cut in half? Or would the rate quadruple? If you chose quadruple, you'd be correct. Again, let's use some simple numbers. For experiment 1, we're going to use 1s in both places, and that would give me K. For experiment 2, we're going to put a doubling of the NO, but not change the H2, and that's going to give me 4K. So we see that quadrupling effect. Now, when we go to our next learning objective, we are going to be able to use this information. They're going to do experiments. We'll see the experimental values. And they'll say, okay, we're doing this experiment. We're doubling the concentration of one substance, and we see that the rate quadruples. That tells me it's a power of 2. So we'll examine that more closely. But for this learning objective, we simply learned what a rate law looks like. We learned about words like order, and we learned that if you have a rate law, you can predict how a change of concentration will affect the rate.